Okay, let's talk about some endocrine pathologies. And endocrine pathologies, in addition to being very interesting, allow us to better understand how hormones function. So we're going to take hypersecretion as our first example, say hypersecretion of a steroid hormone. So normally what happens when a hormone is released, let's say cortisol from the adrenal cortex, that's going to have a negative feedback to shut off the hypothalamus. Hypothalamus releases CRH, which activates the adenohypophysis to release ACTH, which stimulates the adrenal cortex to release cortisol. Elevated levels of cortisol in the blood plasma or inhibit the hypothalamus from releasing any more CRH, because the underlying theory is that there is enough cortisol in the blood plasma to do its job that it needs to do. We don't need more CRH released. But if any of us have ever taken exogenous steroid medication, exogenous means from outside the body. So in this example I just gave, cortisol is an endogenous steroid signaling molecule. But if we ever take an exogenous steroid medication, that introduced medication is going to tell the hypothalamus to stop releasing its specific hormone. Let's just say CRH in this example. So it stops releasing CRH, everything downstream is going to cease to be released in relation to CRH. The problem is if we stop taking that medication cold turkey, the hypothalamus is not up to speed anymore and needs to regain its strength, if you will, to start releasing CRH. That is why when we're taking steroid medications, we have to taper off those medications to allow the hypothalamus to get back on board, start working, and start releasing CRH. If we stop taking that steroid medication immediately, then there's going to be a lag time with the hypothalamus, and that can create problems. Now we're going to look at what's known as competitive inhibition. But there's competition for receptors, and we're going to use the hormone estrogen as an example. Estrogen has receptors throughout the body, and there can be other signaling molecules that compete or even outcompete for those specific receptors. Now, estrogen is necessary for the growth of some types of breast cancer that are known as estrogen-positive breast cancers. The increased levels of estrogen will actually stimulate, it will unfortunately stimulate the growth of those breast tumors. But estrogen also has a positive effect on our bones. That is to say, it inhibits osteoclastic activity, which break bone down. So, if one were to give exogenous estrogen, then hopefully that would help an individual maintain their bone density later in life. So one example of that is tamoxifen. Tamoxifen is a pharmaceutical. It is not estrogen, but it is a pharmaceutical that binds to the exact same receptors that estrogen does. So that's good for bone growth. That is to say, later in life, if individuals have diminished levels of estrogen, they can be administered tamoxifen, which will block osteoclastic activity. Bone will not be broken down, and the goal is to maintain bone density. Tamoxifen is also used for estrogen-positive breast cancers. If tamoxifen binds to those receptors on the tumor cells, then it actually prevents estrogen from binding to those same receptors. In this case, tamoxifen is preventing any tumor growth because it's not mimicking the downstream effect of that signaling molecule binding to that receptor. Okay, let's talk about pulsatile release of hormones. And a lot of this has to do with a concept of downregulation, which I'll talk about in a moment. But a lot of hormones, or let me rephrase this, all hormones are released at very low levels. And one way this is achieved is by a pulsatile release. A little bit of the hormone is released. 1 to 3 hours later, a little bit more is released. 1 to 3 hours later, a little bit more is released. So let's take the hormone GnRH as an example, gonadotropic releasing hormone, which stimulates the release of FSH, LH, and the downstream hormones from the gonads, estrogen and testosterone. If a child is not maturing sexually, and they are given an exogenous form of GnRH, and they are taking it regularly, and it's being constantly released, they don't reach sexual maturation. Now, if there's none released, they also are not going to reach sexual maturation. But if it's released in a pulsatile manner, then they start releasing the estrogen, testosterone, and reach sexual maturation. The problem with a constant release is it causes downregulation of receptors. For example, the anterior pituitary has the receptors for GnRH. If it's constantly being released, essentially the anterior pituitary is becoming hypersensitive to the GnRH signaling molecule, to the GnRH neurohormone. And the anterior pituitary decides, I'm not going to release FSH or LH because there's so much GnRH being released. So that's why, in this case, GnRH needs to be released in a pulsatile manner.